Very good morning, my dear students. I hope everybody is preparing well for your NEET and KCET exams. Students, so we are starting the class in the new platform. So this is already, you know about this platform. So because the number of questions we can solve more instead of taking the classes on the board, the number of questions, and you will understand too. So let's see, we have started the chapter electromagnetic induction. In electromagnetic induction, we have done magnetic flux, Faraday's laws, Lenz's law, and applications, and you have written an exam also on that. Now the topic is motional EMF. Today we are starting from the motional EMF and including alternating current chapter also, maximum we are trying to finish it. All right. Now the topic is that motional EMF. And what is this motional EMF, students? Look at here. Here the magnetic field lines are moving into the plane and there is a rectangular rod is kept here which will have a resistance R. And the magnetic field lines are moving into the plane. Okay, see this into is into the plane. And there is a rod of length L is just moving with a velocity V here. When the rod is moving, initially, imagine the rod is at this point, it is moving like this, see. There is a magnetic flux change linked with the coil. Initially, through this coil, through this area only, the flux, magnetic flux is linked. After some time, see this magnetic flux linked with this particular area is changing. Magnetic flux linked with this particular area is changing. I hope you understand. There is a magnetic flux change. When there is a magnetic flux change, there is an induced EMF will be produced. And what is that induced EMF here, right? You know, that induced EMF here, which is equal to E is equal to B into L into V into sine theta, where theta is angle between L and V. So what is L? This is the length of the rod. V is this one. It is moving perpendicularly. Understand, the velocity of the rod is perpendicular to the effective length. So I'm writing L is not simply the length, it is effective length. And I hope you know the meaning of the effective length, my dear students. Effective length is initial to the final point of the rod. The shortest distance or the straight line distance between initial to the final point of the rod. That's called effective length. Okay, E, this theta will be 90 degrees. Then I can write E is equal to BLV. Right? So this is the formula for the motional EMF. And how many times the question was asked in the NEET exams and in the CET exams, you cannot count, especially in CET exams. For every 3 years, and this question is repeating. This question is repeating. In some of the years, this question as it is given in the next years, right? Based on this motional EMF. Okay, and coming back to this. Motional EMF is done, and how to represent it, we will discuss now. How to represent it. Observe carefully. So by using Fleming's right hand rule. So you all know the Fleming's right hand rule, my dear students, where the forefinger is representing the magnetic field and the thumb is pointing in the motion of the conductor. Automatically, the middle finger will gives you the direction of induced current. Middle finger will gives you the direction of induced current. I hope you got the point here. So let us apply the Fleming's right hand rule, my dear students. So magnetic field lines are into the plane, okay, and the motion of the conductor is right side. And you see, this is what the adjustment I have done. This is what the adjustment I have done. So the the middle finger is pointing upwards. That means this is the induced current direction. And the same is represented like this. Listen. So when the induced current is moving in this direction, immediately you can write a positive terminal and negative terminal like this. In the direction of induced current, the positive terminal must be kept. That is what the induced EMF. EMF means what? A cell. When it is not connected to the circuit, that's an induced EMF, right? See this induced EMF circuit. And imagine this rod is having an internal resistance small r, and this is becoming a circuit now. You can see this is the circuit now, positive terminal, negative terminal, induced EMF, which is equal to PLV, and the current is flowing like this, induced current. So here itself you can write, I is equal to E by R, induced current. So what is E? PLV divided by resistance. What is the resistance? External resistance and internal resistance. Small r plus capital R. So for example, when this small r is far, far less than capital R. So what can I write here? So I can write it. So I is equal to P into LV divided by R. So this is the induced current expression in case of motional EMF. Induced current expression in case of motional EMF. Here, there is another concept called energy consideration. Energy consideration is nothing but, energy consideration is nothing but mechanical energy is equal to heat energy, which is equal to electrical energy. That is called the energy consideration. So energy consideration, you get it, H is equal to I square R into T. For example, if T is equal to 1 second, so what can I write? H is equal to I square. What is I? This is I. Okay. I square. It's a B square, L square, V square divided by R square into R. One R gets cancelled. So what is the heat energy associated with the motional EMF? B square, L square, V square by R. So this is called energy consideration. This is what energy consideration, this one, energy consideration. Now, induced EMF in a rotating bar. Induced EMF in a rotating bar. How simple it is, you see. Induced EMF in a rotating bar. For example, this is what the magnetic field we have, where the field lines are into the plane. Students, where the field lines are into the plane. Right? Field lines are into the plane. Now, there is a fixed point here. There is a rod is rotating in this magnetic field. See, this rod is rotating in this magnetic. So the linear velocity of this is V. This is the fixed point O, and let's say this is fixed point, fixed point. It's A, right? One end is O, another end is A. O is fixed here. Now, this is moving with the velocity V and the magnetic field, and this is the rod. Okay, this is the rod of length L. Induced EMF between O and A, this is half B omega L square. Omega is angular velocity of the rod. Now listen carefully here. Here also, if you apply Fleming's right-hand rule, magnetic field is into the plane and the motion of the conductor is along the linear velocity, and you see the induced current is directed from A to O. Induced current is directed from A to O. So that means I can write this is what the induced EMF, positive terminal and negative terminal. So that means O is at high potential, A is at low potential. So most of the times this question was also asked in NEET and CET. In case of the rotating bar, when it is placed in a magnetic field, where field lines are into the plane, my dear students, where field lines are into the plane. So the point where the fixed position takes place, that is at high potential, the other one is at low potential. So this is a induced EMF in a rotating bar. For example, instead of this rotating bar, instead of this rotating bar, if you take a disc here, instead of rotating bar, if you take a disc, and the induced EMF will be half p omega r square. Just here in the place of length, it becomes radius of the disc. So all these formulas are important. If you're lucky enough, you may get a similar question from this slide in your final NEET CET exam, right? So many formulas are here, right? So this is about motional EMF, energy conservation, induced EMF in a rotating bar. Now, just we'll go to the next slide. 1, 2, 3. Start. A copper disc of radius 1 meter, right? So it is just most of the questions from the second PUC concepts will be based on formulas. So there is a radius 1 meter. It is a disc, remember, and it is rotated about its natural axis with the angular velocity, which is 2 radian per second in a uniform magnetic field of 5 Tesla. The magnetic field is 5 Tesla with its plane perpendicular to the field. Find the EMF induced at the center of the disc and its rim. Okay, so what's the induced EMF here? Is it half b omega r square? Is it half b omega r square? Everything is given. P is there, omega is there, r square is there. And find out and tell me the answer, my dear students. It's just the formula substitution. It is just the formula substitution, right? I hope you got the point. Okay, so let's move on to the next question. You just do this and send me the group, right? Okay. So this is the question was asked in so many times, especially in CET exams, You just check the previous year CET questions and you will be surprised. An aeroplane in which the distance between the tips of the wings is 50 meters is flying horizontally with a speed of 360 kilometers per hour. So now where the vertical components of the Earth's magnetic field is 2 into 10 raised to minus 4 Weber per meter square. Okay, listen, the magnetic field is given as 2 into 10 raised to minus 4 Weber per meter square, and V is given 360 kilometers per hour. Let's convert into meters per second. This is 1820s, and 20 into 5 is 100 meters per second. And at the same time, L is also given. It is 50 meters. Now the question is, what is the potential difference between the tips of the wings? So potential difference is E is equal to BLV. Every data you have, you can do that. 2 into 10 raised to minus 4 into 50 into V is 10 square. Okay, so E is equal to here. So 2 into 5, it's 10. 10 into 0, it's 100. Okay, so 2 into 50, it's 100 into, right, 10 square into 10 raised to minus 4. So this, what can I write? 10 raised to 4 divided by 10 raised to 4. It's how much? 1 volt. Like this numericals will be asked. So nothing else. It is just identification of this particular formula and the unit conversion, nothing more than that, right? Identifying the correct formula and unit conversion, that's it. Okay, let's move to the next one. Self-induction and the mutual induction. So this is also one of the important areas of the chapter. Self-inductance, self-induction. It is the process where magnetic flux linked with the coil is directly proportional to the current. So this is what the inductor, we are not going to discuss what exactly meant by self-induction, what exactly meant by inductor, what is the work of the inductor, those and all the things we have discussed in the regular classes. Now, this is the inductor, okay? So this is the inductor. Inductor is nothing but a solenoidum. So what this inductor will do, you know, it is opposes growth or decay of the current. It opposes growth or decay of the current. Okay, so magnetic flux is directly proportional to current passing through that particular coil. So what the inductor will do, I have told you briefly. Now listen carefully. What is this self-induction, my dear students? And self-induction is that N phi is equal to Li. L is called coefficient of self-induction or self-inductance. So L is equal to N phi divided by I, and E is equal to L into di by dt. Listen. So this is what induced EMF due to self-induction phenomenon. What is that? Induced EMF due to self-induction phenomenon. Very, 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 very important. Induced EMF due to self-induction phenomenon. Right? Now, here, the questions can also be asked from here commonly, my dear students. Do not get confused. And before we go to the questions, I'll tell you one important area here. Listen, this is an inductor. So through this inductor, current I value is increasing. Okay. Now, this particular inductor will opposes the growth of the current. So that induced current will be sent like this. Induced current will be sent like this. Okay, and you know, by knowing the induced current direction, how to find induced EMF, you know, right? This induced EMF is equal to L into di by dt. Students, sign, where is this minus sign here? Minus sign is represented in this induced current direction. Understand? So when this is represented in the form of induced EMF cell, no sign is required for the induced EMF. Remember, while solving the numericals also. In the same way, this is the inductor. So now the current I value is decreasing. What the inductor will do, it opposes the growth and opposes the decay also. It opposes the decay means it should send the induced current in this direction. When it is sending the induced current in this direction, and you know how to write the induced EMF L into di by dt. Okay, so remember. So this is what the induced EMF due to the phenomenon of self-induction. Okay, students. So here commonly the question will be asked. So generally this L is a scalar and it will have the units called Henry. So Henry will become the bigger, that's what millihenry, a microhenry, like that the units of the induction will be, inductance will be there, right? Coefficient of mutual inductance or coefficient of self-induction. So whatever it may be, they will be in the units of millihenries and microhenries like that. So here the question can be asked, the students. Here the questions can be asked. So they'll give you L value. So imagine that is 5 millihenry and di by dt, rate of change of current. Okay. So that is 2 milliampere per second. Like these questions will be asked. And you can find this E value. E is equal to what is that? 5 milli 10 raised to minus 3 into di by dt is what? 2 milliampere. 2 into 10 raised to minus 3. So E is equal to 10 into 10 raised to minus 6. So that is E is equal to 10 by 10 raised to 6. It is 10 raised to minus 5 volt. So this is how the question will be asked based on induced EMF due to the self-induction phenomenon. I hope you are understanding, and now we'll be solving more and more numericals. Okay, and get ready for that. And before that, so there are simple formulas are mentioned here. Just have a look at the formula, students. For a small circular coil, L value, self-inductance, right? L value, self-inductance. What is that? Mu naught mu r n square pi r by 2. So this is L is equal to, generally can be written like this, mu naught n square pi r by 2, generally. Okay, remember this. And here, for the solenoid of length L and area of cross section A, the total number of turns N, it will be written like this. So L is equal to, look at this L right here. So L is equal to mu naught N square A by L. Very important. L is equal to mu naught N square A by L. Okay. For the toroid, it will be mu naught, same, mu naught n square A by L is 2 pi r. L is 2 pi r. Right? Clear? Okay. And here itself, we should know the concept called mutual induction, students. There is a mutual induction. Mutual induction is a very simple topic here. The mutual induction is so simple topic, and let's begin that also. So what is this mutual induction? So when we are talking about mutual induction, there must be two coils. That may be two solenoids, two inductors, and two circular coils. So mutual induction is the phenomenon magnetic flux linked with a secondary coil is directly proportional to current passing through the primary coil, right? Magnetic flux linked with the secondary coil is directly proportional to the primary current. So phi suffix s is equal to, this is n turns, is equal to mutual inductance or coefficient of mutual induction. So into IP. So from here, what can I write? M is equal to n phi s divided by IP. Remember this. And E is equal to minus M into dip by dt. This is very important expression for the mutual induction, which is induced EMF due to mutual induction. This is the formula. Okay, so mostly one question can be asked here in case of mutual induction. Only one question. This is what a solenoid air core only. Okay, so this will have the number of turns N1, the first solenoid. So this is the axis of the solenoid. So exactly the same coaxial axis is there. Another solenoid is kept like this here, which is having number of turns N2. So in this case, mutual induction will be equal to a mu naught N1 N2 A by L, my dear students. Okay, remember. So this is what mutual induction. This is what the mutual induction in this situation, right? So the current is passing through one coil. The magnetic flux is linked with another coil. And remember this formula, and already I have given this formula and this sign convention. Current is decreasing, how the induced EMF will be generated, and small circular coil, how to find self-induction. And for the solenoid, how the self-induction mu naught n square A by L. For the toroid, what is the self-induction, right? So many formulas we have discussed here. Just take a screenshot, right? If you require, just take a screenshot. We'll move to the next one. Okay. Energy stored in the inductor. Students, energy stored in the inductors. So we know the formula U is equal to Li square. So generally, energy stored in the inductor in the form of magnetic energy. In the form of magnetic energy, it will be stored. So that is why it is U is equal to L 1 by 2 into Li square. So this energy per unit volume, so this is equal to a magnetic energy density, my dear students. What is that? Magnetic energy density, which is equal to half into B square by mu naught. Remember, energy density expression in case of inductor, half B square by mu naught. And we all know about the mu naught, which is equal to 4 pi into 10 raised to minus 7 Tesla meter per ampere. This is what we already know. Okay, students, this is energy stored in the inductors. Questions can be asked like this. So from here, U can be directly proportional to L, and I can write U1 by U2 is equal to L1 by L2 when current is constant. When L is constant, I can write U is directly proportional to I square. So then that is U1 by U2 is equal to I1 by I2 whole square. All right. Clear? Now, so this is one part. And the second one is when inductors are connected in series and parallel, what happened to the L effective and what happened to the EM effective? Understand? So that means effective mutual induction, effective self-inductance. What happens? Let us check, right? Let me take another pen here and listen. So this is two inductors. One is of inductance. This is L1 and this is L2. And the induced EMF is E1 and E2. They have connected in series, right? When they have connected in series, L effective is equal to L1 plus L2. Same like a resistor. Resistor will opposes the flow of the current. Inductor will opposes the growth or decay of the current. Okay, that is why it is similar to the resistance only. And as it is connected in series combination, so the net EMF is the combination of EMF across the first inductor plus EMF across the second inductor. The same way, when two inductors are connected in L1, L2. So this is induced EMF is constant here because they are connected in parallel now. So in this case, L effective is equal to L1 L2 by L1 plus L2, and here the point to be noted down. So the total current will split into the two different currents. Okay, I1 plus I2. This is when there is no mutual induction is existed. My dear students, you should remember this one. When there is no mutual induction phenomenon is existed between these two, M is equal to 0, no mutual induction. When mutual induction is there, what happens? I'll tell you, listen carefully. So imagine this is what an inductor of inductance L1. So this is also an inductor of inductance L2. Okay, so imagine the current is flowing through this coil. It will produce a magnetic field, right? That magnetic flux will be linked with this coil. Mutual induction linked between these two, that is equal to root L1 into L2. Understand? So M is equal to root L1 into L2. So for example, if those two coils are placed like this, students, for example, if those two coils are placed like this, see here. So when the current is flowing like this, it will produce a magnetic field, but maximum amount of the flux will not be linked with the coil. See, only little amount of the flux is only linked with this coil. Here, the maximum amount of the flux is linked with the coil. So that is the reason here M is equal to K root L1 into L2. This is L1, this is L2. You know what is this K? K is called coefficient of coupling. Coefficient of coupling, and some cases in KCET exams the questions will come. So K value will be lesser than or equal to 1. It is 1 when exactly both are placed side by side and close to each other. Otherwise it is K value will be lesser than 1. So this is what the general expression, this is what this particular case expression, right? So each and everything we have discussed on this slide is important. I've told you once again, I'm telling you once again, if you're lucky enough, you may get the same question from this slide. Okay, clear? So let's move on to the next one. Yes. So it is a time to solve so many numericals. My dear students, it's a time to solve so many numericals, and let's begin. Okay, the network shown in the figure is a part of a complete circuit and a certain instant. The current I from A to B is 5 ampere and it is decreasing at a rate of 10 raised to 3 ampere per second. Then VB minus VA. Okay, observe carefully. So this is what the battery I'm supplying here. So this is called VAB. Listen, easy way to solve the circuit. And you know, according to the Kirchhoff's rules, all right, voltage across this resistor. See, there is a 5 ampere current is flowing, they have clearly mentioned, and the current is decreasing at this rate. So that means a di by dt is given as 10 raised to 3 ampere per second, and generally current is flowing 5 ampere, right? So now this is given as 5 millihenry, my dear students. This is 15 volt. Listen, potential across this resistor plus potential across this cell and the potential across this inductor. What's the potential across that inductor? E is equal to L into di by dt. Yes or no? So let's, it's all depends on the direction of the current. Okay. Now listen. Now a current I is flowing here from here to here. Loop, let's say it is A, B, you can say it is C and D, A. So the loop of consideration is A, B, C, D, A. So this is a loop. This is our loop. A, B, C, D, A. Okay. Now minus 5 into R. So potential across this one, our loop direction and the current direction is same. Okay, and our loop direction is touching the negative terminal. That means it's plus 15. And this is most important. Current is decreasing. Look at here. Current is decreasing, and I have told you induced current also will develop in the same direction. And you know how to find the induced EMF cell. This is the induced EMF. So what is induced EMF? E is equal to L. See, the sign is not able, we are not required to mention because sign is already represented in this symbol. Okay, L is how much? It is a 5 milli, means 10 raised to minus 3 into di by dt. Di by dt is 10 raised to 3. Okay, so these two gets cancelled. It's a 5 volt, and that 5 volt, listen carefully, we are moving, our loop is moving like this and touching the negative terminal. So that means it's a plus 5 volt. So E value is 5 volts, right? We are touching the negative terminal, that's plus 5 volts. and we are moving like this, like this, like this, and touching the negative terminal. That means plus VAB is equal to 0. Minus 5 plus 5 cancel. And VAB is equal to minus 15 volt. But that's not the answer. No surprise. But that's not the answer. Our answer is VB minus VA. So this is VA minus VB. Okay. So VB minus VA is equal to 15 volt. Like this, the numericals will be asked. Okay, students? Clear? I hope you understand, right? So very, very important expression. It is very important numerical it is, right? Let's move to the next one. Two inductors L1 and L2 are connected in parallel and in a time varying current flows as shown like this. The ratio of currents I1 by I2 at any time t is. The ratio of currents I1 by I2 at any time t is. You know, this is constant, right? The potential across this is induced EMF. And the potential across this also induced EMF. That's constant. So when you write E is equal to IR, similar to this concept, V is equal to IR. When E constant, R, V constant, I can write I is inversely proportional to R. In this case, I is inversely proportional to L. So what can I write? I1 by I2 is equal to L2 by L1. No confusions. Okay. So and here, if somebody asks you to find L effective, and that will be L1 L2 by L1 plus L2 because the inductors are connected in parallel combination. The inductors are connected in parallel combination. That's it. Okay, fine. Let's move on. See, so many numericals we are discussing. That is the advantage of this method. So two solenoids equal number of turns have their lengths and radii in the ratio 1:2. Radii in the ratio 1:2. Sorry, R1 is to R2. And lengths also L1 is to L2 is also 1:2. The ratio of their self-inductances. The ratio of their self-inductances. So we know L is equal to mu naught N square A by L. All right. So solenoids of equal number of turns have their lengths and radii, right? So this I can write mu naught N square into pi R square divided by L. So N is same, mu naught is same, and pi is constant. We can write L1 by L2 is equal to R1 by R2 whole square into L2 by L1. Okay. R1 by R2 whole square, 1 by 4 into L2 by L1. It's a 2 by 1. What is the answer? It's 1 by 2. Like these questions will be asked. Get ready for the questions. Okay. In this way, the questions will be asked. Okay. Let's move on to the next. See, so many questions. Two different coils have self-inductances L1 and L2, right? So L1 is 16 millihenry and L2 is 12 millihenry. At a certain instant, the current in the two coils is increasing at the rate and power supplied to the two coils is same. So power is equal to same. What is power? It's a E into I. It's same. And power is same. And one more. So increasing at the same rate of change of current is also same. Di by dt is also same. Now the question is find the ratio of induced EMF. Okay, we know induced EMF is minus L into di by dt. It's clearly mentioned di by dt is constant. So then I can write E1 by E2 is equal to L1 by L2, which is 16 by 12. 4 3s and 4 4s. So the answer is 4 by 3, which is the induced voltage is 4 by 3. What is the next question? Induced current. So we know power is same. Okay. So EI is a constant. So E into I is a constant. So from here, E1 by E2 is equal to I2 by I1. So what is E1 by E2? It's 4 by 3. So from here, I1 by I2 is equal to 3 by 4. Clear? Now, energy stored in the two coils at that instant. Energy stored formula is half Li square. So U1 by U2 is equal to L1 by L2 into I1 by I2 whole square. Just substitution. L1 by L2 is 4 by 3 into I1 by I2 is 3 by 4 whole square. 3 by 4 into 3 by 4, right? Because 4 by 3, 3 by 4 cancel, and the energy stored in the two coils will be 3 by 4. Students, okay, clear? This way, these models, right? See, still the questions are there. Still the questions are there. We're not leaving anything. A solenoid is of length 50 centimeters. Length 50 centimeters, students. Radius 2 centimeters. 2 into 10 raised to minus 2 meter. And number of turns. N1 is 500. Around its central section, a coil of another turns 50. And mutual induction of the system. What's the mutual induction of the system? So mutual induction of the solenoid, mu naught N1 N2 A divided by L. Everything you have, you can substitute. Mu naught value you know. Number of turns N1 N2 you know. Area also you know here, because R is given, pi R square you can use, right? Pi R square you can use. Now this is L. L is also there. You substitute, you'll get approximately, the answer is 80 millihenry. Find out and tell. Approximately, the answer you get it 80 millihenry. Approximately, you'll get this answer. Okay, 80 millihenry approximately. Okay, is it all right? Now, shall we move to the next one? Next one. See, still it is there. Still so many numericals we are going to discuss so that the complete idea you get it. Two circular coils, one of the smaller radius R1 and the other of very large radius R2 are placed coaxially with the centers coinciding. Obtain the mutual inductance of the arrangement. Obtain the mutual inductance of the arrangement. So look at here, my dear students. So there is two circular coils. Clearly they have mentioned. Okay. One of the smaller radius, let's say this is R1. Another of the bigger radius, that is R2. Now, obtain the mutual induction of the arrangement. How simple it is, let's see. Imagine for mutual induction, what must be the formula? So, magnetic flux linked with the secondary coil is directly proportional to the current passing through the primary coil. Imagine this is my primary coil I2. So due to this current, the magnetic field is produced. B2 is equal to mu naught I2 by 2 R2. Okay. Due to this current, so the magnetic field is produced. And in that magnetic field, there is a coil of radius R1 is placed. Now, when this current is variable, there is a magnetic flux linked with the first coil. Understand? Magnetic flux linked with the first coil. What is that? So B, magnetic field due to the second into, right, area of the first one. So what is B2 here? Mu naught I2 by 2 R2 into area of the first coil is what? It's a pi R1 square. Simple. right? So magnetic flux here. So this is what I'm going to write. Magnetic flux linked with the secondary coil is equal to mutual inductance into current in the primary coil. So what we'll get it? Phi1 is equal to M into current in the second coil. This is what the primary coil we have considered. Okay. And when you compare this equation and this equation, phi1 is equal to I2 I'm writing separately. Then what is left? So mu naught pi R1 square divided by 2R2. Sometimes the questions will be asked like this, my dear. Okay, let me write. So this is the mutual induction, right? Mutual inductance. So M is equal to mu naught pi R1 square divided by 2R2. So mutual inductance of the arrangement is directly proportional to R1 square by R2. Sometimes these kind of questions also will be asked. It's more like theoretical, but according to the options you should go, right? Clear? So this is about mutual induction also. Now we'll move to the next. And the last concept of this electromagnetic induction is the AC generator. Last concept of this is AC generator. So what is this AC generator? Which works on the phenomenon of electromagnetic induction. What is electromagnetic induction? Whenever there is a magnetic flux change, there is an induced EMF will be produced, right? So now in this AC generator, so how the energy will be converted? So mechanical energy will be converted into electrical energy and AC alternating current generator. Okay, and E is equal to E naught sine omega t. That's an induced EMF. This is the peak value of induced EMF. And if you divide this with R and you get it, I is equal to I naught sine omega t. Okay, so where I naught and epsilon naught R E naught are the peak values of EMF, are the peak values of current, my dear children. Peak value of EMF are the peak value of the current. And you know, IRMS is equal to I naught by root 2 and ERMS is equal to E naught by root 2. When you have the peak values, right, you can find the IRMS values. Remember, you can find the IRMS values when you have the peak values. I naught by root 2 and ERMS is E naught by root 2. So this is about AC generator, and about the parts and the working. It's not at all required for us. If you want, you just go through your second PUC or class 12th books. All right. Okay, so this is the end of the electromagnetic induction chapter. Now we will begin alternating current chapter also right now.